Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on Math Basic Course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into section 4.4 in the Big Ideas Math Integrated Math 1 textbook on scatter plots and lines of fit. Now, these sound a little bit foreign, and they probably should. This is more statistics based. This is still in chapter 4. This has to do with writing linear equations. It still is the algebra stuff that we built off of earlier, but now we're going to have kind of a statistics mindset to it. Not in full. We're not doing like mean, median, mode and things like that, but things that you would do in statistics classes with this algebra material. And I believe section 4.5 does a little bit more of that as well. I'm just going to jump straight into it. So download the PDF in the description section down below if you'd like to follow along with that. Otherwise, just watch the video here. I'm going to start with the lecture portion. And if you want to get to the problem set numbers 1 through 24 only, you can find the timestamps in the description section down below for the problem set. Without further ado, I'm going to go ahead and get started. We're going to interpret what are called scatter plots. It's basically just a bunch of points. I mean, they're made from data, but use that stuff and interpret them. Come up with what they mean, y-intercept, slope, things like that. Identify correlations between data sets. You might have heard this word correlation before, not just in math, but in English. If things correlate, maybe there's some sort of link to them, and I'll talk about that a lot more. If the book doesn't talk about it, you'll obviously hear me have a lot to talk about it. And use lines of fit to model data. A line of fit is the best line, not a curve, but the best line you can draw that goes through your data points. So there it is. Okay. Those are all new words for us when it comes to the textbook and such. So we're going to see what it says. Interpreting scatter plots. So a scatter plot is a graph that shows the relationship between two data sets. So some sort of X and Y. It can be time and score and things like that, right? Or time and temperature, whatever it is, time and money. The two data sets are graphed as ordered pairs in a coordinate plane. Scatter plots can show trends in the data. So by a trend, you can say, as X increases, what do you tend to see with Y? And because we're only doing things in a linear basis, we're probably only going to see ones that are linearly based, meaning not too many things with curves and things like that. Or we'll talk about them just to say that they're not linear. We'll see. So example number 1, interpreting a scatter plot. The scatter plot shows the amounts X in grams of sugar and the numbers Y of calories in 10 smoothies. So as X increases, and they're doing something interesting that I want to bring about on the scale as well. I should probably do this more often, and I'll try to, I suppose. They're going to fit within this window range. You can see that the lowest number of grams they have in sugar is around 50, a little more than 50, and the highest looks to be 70. So they change their scaling on their graph so that, look, these go by 4s, but they don't go all the way down to 0 in that way. They basically just show this little thingy right here that says from 0 to, all this stuff up to 46, irrelevant. It's not going to be there. I'm going to start probably doing that with my graph in 0 to 240 if it fits within a tight window range that's not close to 0. Anyway, what you're seeing is a bunch of points here that's like, hey, I have this many grams of sugar in my smoothie and this many calories, etc. X and Y. So X isn't always time, as you can tell. It asks how many calories are in the smoothie that contains 56 grams of sugar. So we try and find the 56 between the scale 54 and 58. It's right here, and boom, it's this guy right here. That's 270 calories. So you can see right there, the smoothie is 270 calories. Oh, there are some points right there. I missed it. Part B, how many grams of sugar are in the smoothie that contains 320 calories? So we find the 320 calories one. They're pointing to that one right there, and that's the one with 70 grams of sugar. That's part B. Part B says, what tends to happen to the number of calories as the number of grams of sugar increases? So as X increases, what's happening to Y? We tend to see a trend that tends to increase as well. Is that always the case? Not necessarily. We see that 56 grams of sugar one has less calories than the 54 grams of sugar ones do, but then again, there's more than one there, and that makes this not a function if you're talking about the relation here. But we're not really talking about that. We're just talking about just the trend. As an overall trend, you see this up and right pattern as this goes. Is it a very strong fit? It's okay. I definitely see that trend, and I believe it. But as you can see, you can have multiple different sets with different grams of sugar have the same calories, because it just depends on what they're doing with the drink, right? It just varies. But that's what they're saying. As the number of grams of sugar increases, the number of calories increases. As what it tends to do. That's your overall trend there. Identifying correlations between data sets. So a correlation is a relationship between your data sets. You can use scatter plots to describe them. We can see a positive correlation here. As X goes up, so does Y, and a negative correlation here. As X goes up, Y goes down. So you'll know that positive correlation also has to do with positive slope. So up and right is a positive slope, down and right is a negative slope. And I say this a lot. Negative doesn't mean bad. It's just It's just the negative slope. Y goes down as X goes right. That's all that we're thinking of there. And this is no correlation. There's nothing really that you're seeing as some sort of trend, or if there's a correlation, it's absolutely weak. You know, when it comes to drawing a line, we're going to talk about lines of fit later, but I can draw a nice positive slope line here, a nice negative slope line here. There's nothing here that I can tell that should be this curve or this line here versus any other line that I could draw. How is this any different than this one when it comes to a line that's fitting through these points best? There really isn't one. There's no correlation among these points. It's totally untrendy, if you will. So identifying correlations, tell whether the data shows a positive, negative, or no correlation. This first one, clearly there's no actual pattern here that you see where something is, you know, as X goes over, how does Y go? And what was this relationship, by the way? Age and vehicles owned, how old you are and how many vehicles you've owned, which is kind of interesting. I mean, I've only owned 2 vehicles in my life, but it's interesting. You'd think that the older you are, the more vehicles you've owned in your life, but maybe some people traditionally keep. I mean, look, this is a small sample size, but there's no correlation. There's no correlation in this set here. And by the way, I'll state it more than once, and I'm sure the book will state it at some point. Correlation doesn't mean causation. What that means is just because one happens, just because there's a relationship, doesn't necessarily mean that one causes the other to happen. It could, but there are other variables. Temperature and coat sales at a store. Average daily temperature as it goes up, you can see that the coats sold per day goes down. Okay, and that makes sense, right? It doesn't necessarily mean it caused it, because there are still some sales. Because it could also be the time of year. It's not just the temperature, it's also time of year. Maybe I just buy more coats in the winter in general. Anyway, so as the temperature increases, the coats sold per day decreases. You can see there's a negative correlation there. There is a correlation, and it's a negative slope. So that's what we're saying. No correlation for the first, negative correlation for the second. I'm going to skip these. However, I will state that these ones aren't yet graphed, so we're going to have to make our own graph. When they say make a scatter plot, we're going to have to plot our own points. So I'm sure in my own example, or in the problem set, we're going to have to do something like that. Okay, lines of fit. I've kind of already mentioned this a couple times. I've drawn my own lines here. But when you see some sort of correlation, positive or negative, you can draw a trend line, a line of fit. That is the line that most closely fits through your data points. It doesn't necessarily have to touch any of the data points, but it just needs to be the one that seems to show the best trend, so I can make better predictions on my data that model, from my line that model that data. So using a line, first of all, you make your scatter plot by plotting your points, and it looks like we're going to have to do some of it here. Decide whether it can be modeled by a line. Is it positive, negative, or no correlation? That's different from, no correlation is the same as a correlation of 0. And by the way, I think the book's going to be pretty obvious with it. I don't think they're going to kind of make you guess. This is your first time being exposed to it, so they really want to let you know. And you draw a line that models it closely, right? Positive slope for a positive correlation, negative slope for negative correlation. There should be approximately as many points as above the line as below it. So we'll try and do something like that. Use your ruler. Write an equation using 2 points on the line. So what we started to do, here's where earlier in the chapter has to do with what we did. Point slope form is going to be a big key in what we do. Unless you find a point that's good on the y-intercept, point slope form, use 2 points to come up with the slope, and then make a line based on it. Again, the points do not have to actually represent data pairs, but they must lie on the line of fit. So you pick 2 points as best as you can based on your line. So here we go. Here's an example. It says the table shows the weekly sales of a DVD and the number of weeks since its release. Write an equation that models the DVD sales as a function of the number of weeks since its release. Interpret the slope and y-intercept of the line of fit. So as the weeks go on, you can see that the cost, or the number of sales in millions, I should say, $19 million in sales and 15, etc. They go down over time. That's normal. I'm used to that. So we can see here the graph. First of all, you plot the points on the graph. Okay, 1,19 we see right there, and 7,7 I see right here. So they're plotting all the points, and then they drew themselves a trend line, a line of fit, the line that seems to best work through that. If I drew this line, I would disagree that this black line is a better fit than the blue line that they show right here, or this line right here. Okay, that line, even though it's the same slope, it doesn't go through the points quite as well. And as they said, points below and points above should be about the same. I have 3 points above, 3 points below, and 2 that seem to be on the line. Now, we'll do the best we can. This is a little interpretive, and you kind of make it up as you go. You do the best you can. Now, the way that they made theirs, they're probably going to come up with pretty clean numbers. So we're going to see if ours do that as well. I'll try. I haven't done the problems yet, so I'll try. Otherwise, we're going to deal with weird fractions, weird decimals sometimes. So what did they do? They picked 2 points that actually appeared to be on the line. Now, it seems that all of their points, like all of these points right here, they could have chosen any of these ones as well because they're pretty good like integer values, and any of those would really give them the same line, right? It's part of the same line. But 5, 10, and 6, 8 for x and for y, x1, x2, y1, y2. And then they come up with the slope. They get a slope of -2. Now, I don't know if we have to interpret that. We probably, if they don't, I'm going to oh, it looks like they do later. And then they use point slope form. They choose one of the points, either 5, 10, or 6, 8. Looks like they chose 6, 8. Plug them in for x1, y1, and they came up with the slope-intercept form from that by distributing the -2 and adding 8 to both sides of the equation, as we've done from previous sections. I believe it was 4-2 that we were writing from point slope form to slope-intercept form. So you get an equation y equals -2x plus 20. Now, if we interpreted that, what would that say? Well, slope, the sales are decreasing by about $2 million each week. Down 2 over every 1. 2 is in millions of dollars. Down 1 is every week. Boom. The y-intercept has no meaning because there are no sales in week 0. So that's kind of interesting. I was wondering if they were going to say that was the first week or opening week, and then 1 week later it's $2 million down, but it sounds like they're saying week 1 is the true sales beginning. They probably even said that and I missed it. No, number of weeks since its release. I don't know. I could have argued that that was the opening week sales, 20 million. And that's something that we can predict. And of course, they can ask us to make predictions. What about week 9? We can plug in 9 into here and make a prediction for what it would be. Oh, we predict, based on the graph, it would be $2 million in sales and things like that. Okay, that is the end of the lecture portion. Let's go on to this set here, numbers 1 through 24. We're going to begin with the vocabulary and core concept check. It says, when data show a positive correlation, the dependent variable tends to blank as the independent variable increases. Remember, independent variables x, dependent variables y, with a positive correlation is as x goes right, y goes up. So also an increase. They tend to increase. Vocabulary number 2 is, what is a line of fit? A line of fit is a line that best fits your data. A trend line. Oh, I guess that's 2 words. A trend line that models your data points when a correlation is shown. So it's the line that best goes through your points, the one that says this is the best thing for the model. That's the way I'm going to say it right there. And I like to bold it to make it stand out, but I'm going to move forward. So guys, numbers 3 through 24, we're going to begin this thing. I will be attaching graph paper below, as it seems like we're going to have to do our own graphs for our for the tables that they give us. We'll see how I have to change the scales around, and hopefully we come up with good like fraction or integer trend lines with equations, because otherwise these can get a little wonky. So we're going to go ahead and get started right here. Hold on, let me get to the next slide. Okay, let's begin. In exercises 3 through 6, use the scatter plot to fill in the missing coordinate of the ordered pair. Now this is just as simple as making sure you know how to find points on this thing, and that you can work with a scatter plot. Okay, so these should be pretty simple. On number 3, we have 16 comma blank, and we have to come up with what that is. So 16 is the x value based on scale. These go by 2s, 12, 14, 16, and there's only one individual point right there. That is when you have a y value of 6. So I'm going to put it in a different color like that. Number 4, we have 3 comma blank, another x value. So x, this is an odd number, which will be between 2 even numbers that we have. So basically, again, understand the scale. These go by 2s, 2, 4, so 3's in between. So we're looking at this value here. I guess I'll do them in green. That's a y value 14. So 3 for x, 14 for y. Number 5 now shows us y values. So they have a y value of 12. We have to find the x value that goes with that one. The 12 is between 10 and 14 right here. There's only one x value that belongs there. And that is an x value of between 6 and 8 is 7. So this is 7 comma 12. So boop to boop to boop. We got that. And then number 6, blank comma 17. Let me write it first. So on this one, 17 is between 16 and 18, and it's this guy right there. And that is an x value between 6 and 10. The x value is 8. So that is 8 comma 17. There's no context to those problems. They're just making sure we can fill those in because they're going to ask us questions for us to do those things based on context, probably coming up. Number 7, interpreting a scatter plot says the scatter plot shows the hard drive capacities in gigabytes and the prices in dollars of 10 laptops. Okay. Let's see. So, hard drive capacity in gigs. We got 2 gig, 4 gig, all the way up to 12 gig here and how much they cost. $1,400 one, things like that. First one, part A, says what is the price of the laptop with a hard drive capacity of 8 gigabytes? So this is no different than what we just did, but 8 gigabytes leads to how many dollars, right? How much money? So what we have to do is just basically find the one that goes with that as an ordered pair. 8 gigabytes is our X, and there's only one Y value for that one. It's between 1,000 and 1,200, 1,000 and 1,200, and that's 1,100. I'm going to say is what that one's supposed to be. So there it is. That's part A. Part B, what is the hard drive capacity of the $1,200 laptop? So go to Y value of 1,200, boom, right there, and find the one. That's the 12 gigabyte one. Is that the only 12 gigabyte one? No, but that is the $1,200 one. It has 12 gigabytes. So $1,200, so not a function in this case, but leads to a 12 gigabyte laptop. So if they ask you, what is the cost of a 12 gigabyte laptop? I mean, we don't have the function version of that because there are 2 answers. So there's this or that. Part C, what tends to happen to the price as the hard drive capacity increases? We see this upward trend. I know we're not doing lines of fit right now, but we see a positive trend there. So as X increases, Y increases. So the price tends to increase as the hard drive capacity increases. Put HDD. That's hard drive shorthand for you. Okay, that's number 7. Number 8, interpreting a scatter plot. The scatter plot shows the earned run averages and the winning percentages of 8 pitchers on a baseball team. Just so you're aware, the lower the earned run average, the better for pitchers. They allowed less earned runs over the course of 9 innings, which is how they kind of do calculations. So winning percentage, higher winning percentage, better, right? But higher earned run averages is worse. Okay. So anyway, what is the winning percentage of the pitcher with an earned run average of 4.2? And normally they use 2 decimal places for ERA. They would say 4.20 generally. Okay, so 4.2. Here's 4. Here's 5. Here's 4.5. So the 4.2 must be this guy right here. So the pitcher's winning percentage looks to be 600. They don't say 0.660. They'd say a 600. Well, let's see. What would they say? I guess I'd say 600 winning percentage. Anyway, so for part A, again, a 4.20 ERA. Because, yeah, I think they say 500 winning percentage for that stuff. It's weird how we say numbers in baseball, despite the decimal. So 600. I'll put winning percentage. Not to be confused with wild pitch, by the way. Part B. What is the earned run average of the pitcher with a winning percentage of 330? So 0.330, here's 300, here's 400. The only one in between is clear as day is going to be that one. They have an ERA of 5. So this is like number 7. It's just a different kind of question. So 0.330 winning percentage. You got a 5 ERA. I'm going to put 5.00. It's pretty high. 4.2 is actually, I'm not going to say it's high or low. It's probably a little worse than mid. You want to be in the 3s. If you're in the 2s, you're doing very well, but you want to be in the 3s, ideally. Part C, what tends to happen to the winning percentage as the earned run averages increase? So, as I stated, ERA goes up's a bad thing. You've allowed more earned runs over the time. You're likely to see less wins, and you can see with this trend here, it's decreasing. And negative doesn't always necessarily mean bad, but in this case, it kind of does. It's just telling the information as it is, though. So, the winning percentage tends to decrease. Pitcher winning percentages tend to decrease as their ERA, earned run average, increases. So the answer is decrease. Okay, number 9 through 12. Tell whether x and y show a positive, negative, or no correlation. They're not asking me to explain it, but I'm going to draw a trend line if I tend to think that I see one here. It doesn't have to be strong. It just needs to show some sort of correlation. It can't be weak, though, either. So on number 9, I'm seeing this upward trend like there. Again, we're not really drawing trend lines. I'm just giving you the idea of it. So number 9 shows a positive correlation. Positive slope means positive correlation. Number 10, I'm not seeing a trend. I don't know if you are. You're like, oh, yeah, you can draw it like this. No, I'm not seeing a trend. There's a true scatter of these things. And contextually, numbers 9 and 10 are hard for me to... Really, 11's the only one that I can make sense of contextually when it comes to just first quadrant values. When we're talking about negatives, it's hard to talk about contextually what we can even talk about it here. Anyway, number 10, I see no correlation on this one. I'll just put no. No, I'll put no correlation. So that's my number 10 answer. Number 11... Number 11, I also see no correlation. Even though it's all in the first quadrant, like I was stating right here, at least we could probably provide context for it. There's no actual trend here. As x increases, we're not really seeing y increase. Plenty of y's that are down here, and x's down here show good positive y's. It's scattered. A true scatter of scatter plots, and I forgot to move these over. Number 10, number 11. True scatter, once again, no correlation on number 11. And number 12... not the strongest of negative correlations, but it truly shows a negative trend through this thing. Did I draw the best trend line? No. But it's showing one that's negative. Negative, with the negative slope. Just like the ERA one, with winning percentage. Okay. Halfway home. Numbers 13. Well, these are going to be longer, I'm sure. In exercises 13 and 14, make a scatter plot of the data. Tell whether x and y show a positive, negative, or no correlation. So this is where graph paper is going to be used. Okay, I just found some. Copy and paste. And best thing I can do really for this is we're going to use the first quadrant, but determine scaling. These all fit between 0 and 5 for both x and y. So I actually feel like I want to make these go by every 2 is going to be a 1. So I'm going to change the scaling like this. I hope that's okay. So this is like 5 and 5. This is like 2.5, for example, things like that. So this is 0.5, 1, 1.5, 2, 2.5, etc. Okay, so we have x is 3.1 and y is 1. So here's 2.5, right? 3.1 is sure right there. Remember, y is 1 is right here. So I'm going to do that. Let's see. I guess that's decent enough. 0 for y is x is 2.2. 1, 2, 2.2, and 0. Now again, there's no context for these things. We just got to plot the points. So 2.5 exactly on here, 1 exactly on here. So here we go. All the y values are exactly in integers, but I get to spread them out more, and they get to stay with x in the same kind of scale. I won't mess up that way. Here's 3, 3.5, and 3.7 should be about right there, whereas y is 2. So right here. And then 3.9, a little farther over, as y is 0. So far, maybe a positive trend. Otherwise, there might be no trend here. I don't see a negative trend just yet. 1.52. Okay, now I'm looking more at no trend, but we'll see. We'll see. 2.73. 2.52. Yeah, this looks pretty scattered as far as scattereds go. And 2 and 2. 2.0, 2.0. Did I miss any? 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Okay, I think I got all 8. All right, when you guys look at these, do you see a trend? I do not. I see no trend, no correlation, whatever you want to call it. What did I say positive? I'll say no correlation. Now, did I know that until I looked at the table itself? I didn't know that. You know, it would help if I wrote these in order, in increasing order, and saw an increase in y, but I think visually with this, it's going to be easiest to tell. Number 14, I'm hoping to see something that's not no. And in fact, this actually does, speaking of what I just mentioned, look at your x's and your y's in the table itself and tell me what you see. X's are increasing. The y's as a trend are decreasing. Despite the fact the first two are the same, I'm going to guess this is a negative correlation. It just kind of makes sense here. Now, what I do have to change on this one is my scale on y's. My x's can go by 1s. My y's probably just want to go by 10s. Doesn't matter that this goes up to 100 that way, but and 50 and things like that, even though my top's 67. I think I'll fit what I can best here. So when x is 3, y is 67. Here's 60 and 67. When x is 4, y is also 67. But then it starts to go down pretty sharp. When x is 5, y is 50. Boom. When x is 6, y is 33. 33. 7, 25. 8, 21. Just above 20 a little bit. 9, 19. Not much less than 21. And 10 is 4. Like that. Clearly a negative trend, right? There's a negative correlation there. I'm just going to write negative. And hopefully you can see the same thing on that. Not straight, right? We're not going to have perfect relationships like that. But okay, number 15, modeling with mathematics. Now we have context, okay? The table shows the world birth rates Y, number of births per 1,000 people, X years since 1960. So when it shows X is 20, that means that's the year 1980. When it shows 22.4, that's 22,000, let's see, 22.4 births per 1,000 people. Okay. Let's see if we can interpret that stuff in a bit. They say part A, part B. Number 15, we have the table that said write an equation that models the birth rate as a function of the number of years. In order for us to do that, we are going to have to plot the points in a scatter plot. We're going to have to draw a trend line. Now, this is going to be a little tricky and tough for me when it comes to this. Now, what I'm looking at for Y's, I'm going to do the best I can. When I'm looking at Y's, what I see is the lowest is 20 and the highest is 35. If you don't mind, what I'm going to do is treat this. I'm going to even hide away the other axes to make this even easier for us to not look at them. But I'm going to make the Y's, listen, they'll go by a certain amount, but they're going to start not at 0. This is going to start at 20. 20 is going to be the bottom. And if you don't mind, I'm going to make 40 the top, which means these go by 2s. So this is 30. So 22, 24, etc. I'll do that for Y. X's, I wanted this to be 50. That means those go by what? 5s? So this is 25 right here. So it's starting at 0 though. This starts at 0. So this is going to be a little tricky there. I'm starting at 20 for Y on the bottom. I hope that's okay. So when X is 0, Y is 35.4. Here's X is 0 and 32, 34, 35, getting close to 36. Probably about right there. Okay. Now, since they're making us draw this trend line thing, here's 5, 10, when X is 10, I'm guessing there's some sort of correlation, positive, negative, whatever. It looks like it's going to be a negative correlation. But 32, 33, 33.6. Wait, that would be closer to 34, huh? Let me think about that. 32, 33, yeah, probably about right there. When X is 20, Y is 28.3. So here's 28. This is a little tougher to do this without, oh, that's a little high up because 29 is in between. This is kind of tougher to do. When X is 30, Y is 27. Now that's 20, 22, 24, 26, 27. When X is 40, Y is 22.4, so 22, and 23 is in between there, so 22.4, maybe about right there. And when X is 50, Y is 20, so boom, right at the bottom like that. Now I'm going to draw a trend line. Now what you would have to do, see, I have the, line tool, right? Actually, that was pretty good. I just drew it pretty fast. But I have the line tool. You have a ruler. Do one, hopefully a clear ruler or something like that, because you can kind of see on the other side what they are, and do your best form of trend line. I just made that up super fast. I didn't mean for it to look probably as good as it does. That's actually not bad. Maybe if I do a little bit more upward tilt, I can generate some better points, because I think they want us to make a good trend line out of this, right? Not random weird numbers. That's actually not bad. The fact that it goes through this point means it's a point that I can use, like 50, 0. It doesn't seem to go through any of my other points, but it does go through like other points as a whole, right? It goes through this point here, as it appears, that's 25, 28. 25 for X, and that's 28 for Y. Or this point all the way up here, that would be a Y-intercept, which would be even easier, or better for me, 0, 36, like that. And I think these are all falling in the same line. I'm not doing an estimation there. Those seem to fall on that, and that's probably what they designed for it to do. I have no idea, but I think it'll at least come up with clean numbers for us. So if we did want to use the two best points possible, Honestly, further away points tend to lead toward more accuracy, but because these are actually on the line, doesn't matter. But since that's a y-intercept, maybe for one problem, I'm going to use slope-intercept form by actually using this y-intercept. That means we have a b value truly of 36 without having to use point slope form. But we still have to find the slope. The slope is still our y2 minus y1 over x2 minus x1. Like, we're going down 36 and right 50, literally. Like that, negative 36 over 50. And as a decimal, that would be what? Negative 0.72? Is that right? Negative 0.72. So I can use that as my number for that. Okay, that's just my call. That's how I went with it. Now, is that a good trend line to us? I guess there are 2 points that, oh, you know what? I don't know if that trend line's good enough. Because I have 3 points that are below, 2 that are above. Should I change it? I don't know. Those points look pretty okay. I guess that would probably be a better trend line like that, but then I don't know what points it goes through as well. I'm going to leave it. It's probably not the best version of one, but let's just go off of what I'm saying with it. It's kind of opinionated. It's not truly. There's an actual true line of fit, but we're not calculating that way. But we are coming up with the equation. So my equation is going to be y equals mx plus b, negative 0.72x plus 36. That's just what I'm coming up with mine. And that is part A when they say write an equation that models the number of years since 1960. Now they say interpret the slope in y-intercept. So my y-intercept of 36, you have to remember that y represents the number of birth, the birth rates, the number of births per 1,000 people since 1960, and x equals 0 is the year 1960. Now remember, this is only interpretive for a model. We actually have a data value of 35.4, but for the sake of our equation, our interpretation of 36 means the number of births. Let's see, there were approximately 36 births per 1,000 people in the year 1960. Now that's my y-intercept interpretation. That was y-intercept, by the way, not slope. The slope is the negative 0.72. Now, we had one version of it that was down 36 over 50. That's every 50 years. The number of births. Wait. Yes, the number of births per 1,000 people is decreasing by about 36. We have the negative 0.72, though, as well. So we can say for the slope, let's see. This is going to be tough because there's a per on this actual y value as well. The y itself is a rate, it's not just a quantity. We are losing, let's see. Every year, the number of births per 1,000 people decreases by about 0.72. You decrease about 0.72 births per 1,000 people every year. Okay. Or over 50 years, 36 births per 1,000 year decrease. Okay, let's go to number 16. Same thing, different model, okay? So we have to do the scatter plot, the graph, all that kind of stuff. So number 16, we got what? X goes 1 through 6. I think I'm good keeping the x's as they are. Y jumps from 0 all the way up to 113. I'd almost be okay making this 100 and going up by 10s just by putting that 113 just kind of off the grid. It's going to be a little close to 110, so let's just do that. These are going by 10s. These are going by 1s. When x is 0, y is 0. Perfect. When x is 1, y is 18. Here's 10, 20. So 18's 4/5 of the way up, like that. 8/10. 2 comma 40. Looks like a positive trend, right? 3 comma 62. 4 77. 60 70 77. 5 85. Here's 80. 85's halfway in between. And 6 113. This is the one that's going to go off. So here's 100. I'll say 110, maybe 113 about right there. So did the best I could given how I went for scales. I'm going to do a trend line this time. Let's see. I'll have to fix it, obviously. But let's try and do as many above as there were below. I don't think my last trend line was actually very good. Now, I'm not trying to specifically go through any points. I'm just trying to make sure that I kind of have some above and below. I seem to have more below than I do have above, so I either have to just kind of mold it the way that looks best to you with that. Maybe something like that. Is that a decent trend there? That one kind of becomes an outlier, but 1, 2 below and just like 1 above, the rest are kind of on in such a way that it actually seemed to strike some points. I actually think this is going a little bit below the 0, 0, but this was unintentional. I actually made it go through this point pretty well, so I can use that one as an exact if I chose to. And then this one right here as well. So those actually seem to be 2 good points because nothing else really seems to go through grid lines well. So I'm just going to choose these 2. I have this point that's 1, 18. And this point here that was 4, 77. So with those 2 in mind, maybe the numbers might be clean, but I don't know if they necessarily produce a good fraction, a good decimal for my slope. I have no idea. And this time I probably want to use point slope form to come up with it. So let's start with the slope. My slope is my rise over run from 18 to 77. What is that rise from 1 to 4? What is that run? Clearly that's going to be a run of 3. 77 minus 18 is 59, so I don't think this is a very clean number. I might round it though, if you don't mind. I don't want that to be like, like that. So what if I said around 20? If it's okay, I'm going to kind of, because 60 over 3 would be 20, right? Listen, if this becomes anything if I change the trend line even slightly, then I can force it to be 20. So I'm going to pretend like mine was around 20. Otherwise, this gets a little weird. Right now we're talking about this point, it just gets weird. So let's just say it's around 20. For the y-intercept, I'm going to be using point slope form. Let's choose like the 1, 18, right? So like y minus y1 equals m times x minus x1. If I distribute the 20 over and add 18, I'll get y equals, whoops, that doesn't cross out actually. I'll get y equals 20x minus 2. Now the minus 2, what's the context here? The table shows the total earnings, y in dollars, of a food server who works at X hours. I'm curious, if I just went ahead instead and said that it hit through the 0, 0 would be perfect, but that's an idea of how I said my trend line looks like it's going slightly negative. So 20x minus 2, I would have loved if it just said y equals 20x. The plus 0, because 0, 0 is literally a point. It almost would make sense to do that. So if I forced a different answer, I would say y equals 20x. I mean, how much error was there? Very slightly, very little. It probably isn't right for me to take away the minus 2, but I kind of want to do it. Because remember what I did, right? I changed my slope. I changed it from, hold on, what's 59 over 3? Let's do this. Excuse me. I'm going to use 59 over 3 with the same model. And if I add 18 to that one, it doesn't change it very much. Okay. All right. I'm going to say y equals 20x, guys. I know it's approximated, but it makes for cleaner answers for interpreting things. Normally, you can't force things like that, but being so close as to what they were, I don't think it's actually a problem. So that was actually part A, write an equation. Now, this was all about, the table shows the total earnings in dollars of a food server who works X hours. You work more hours, you make more money. Because you can't make negative money by not working any hours, so I don't want to interpret it that way. Let me clear my throat. Hold on. Okay, hopefully I'm good there. Hopefully I sound a little better. I went to an amusement park yesterday, did a lot of yelling, a lot of screaming, so I'm going to kind of come off that way. Interpret the slope and y-intercept of the line of fit. I'll start with the y-intercept again because it's 0 for the way that I forced it. Otherwise, again, negative 2 would be a poor. If the server didn't work any hours, they would lose $2. No. See, there's a point that's 0, 0 on there anyway. So a food server who doesn't work any hours will not make any money. 0 hours, $0. Now the slope says every hour, remember X is hours, every hour, a food server will earn approximately another $20. Well, just say $20 because every hour. So there's the rate, right? 20 is Y is your rise, and that's dollars, and X is hours, that's your run. So rise 20, run 1. That's what we're saying right there. Okay. Number 17, open-ended. Give an example of a real-life data set that shows a negative correlation. You want to think about, as you increase something, what decreases over time, and or what tends to decrease over time. Not necessarily a cause, but you can say that. You could say something like, I'm trying to think of something with regard to energy, like number of. Let's see if that goes down. Okay, I'll do this. A runner's number of minutes running, X. So that's the independent, how long you run, versus, not necessarily against, but just what it's compared to, versus their average speed, average running speed in miles per hour, and that's Y. So that would be negative, probably, because what would happen is over time, you'd probably lose energy, right? Maybe you start faster and then you slow down. That's not necessarily true. I tend to, knowing how long I'm going to run, I tend to kind of set a tone and set a speed and kind of keep that pace. But we can just say it that way. We can just state that it's not that they slowed down as time went on. We could say somebody set their time to just run for 5 minutes. They're going to go considerably faster, whereas someone else runs for 5 hours. I don't know if you're going to run for 5 hours, but if someone ran for 5 hours, they would set their speed to be significantly slower. So it doesn't have to be the same runner and their data points. It could be different runners or the same runner at different times. I think that works. I think that's a true negative correlation in my book. Number 18, making an argument. Your friend says the data in the table show a negative correlation because the dependent y variable is decreasing. Is your friend correct? Explain. Well, I'm not going to plot these on a graph just because scale and all that stuff. It's going to take a little bit of time. But remember what I stated that one time on this very first one? The x's weren't in order. And if I put them in order, I could probably see that there was no trend in y because it was all some up, some down, things like that. This one, the x's are clearly in reverse order. The x's are decreasing. And as the x's decrease, the y's decrease. That would also mean as the x's increase going to the left, the y's would increase. So your friend is stating, because y is decreasing, it's a negative correlation? No, because the x's are decreasing at the same time. So my friend is incorrect because the x's are decreasing as the y's are increasing. Which is another way of saying that the y's would be increasing as x's are increasing. Therefore, the correlation would be positive. It's all about slope. That would be a positive. Remember, a graph, and this goes perfectly with when we started talking about slope. I would ask people, what makes a slope negative? And people would say, if the line goes down, if it goes down. No, because all, except for horizontal lines, right? All graphs go down, okay? Let's look at two lines. Here's a line, there's a line. Do both of them go down? Yes. But this one goes down as it goes right. That's what makes a negative thing. This goes down as it goes left, or up and right. Up and right is positive. Down and left is also positive because it's negative over negative. So I know I'm spending more time on the problem than I need to, but I just want to make sure that it makes sense. It's not just that y decreases, it makes it negative. It's as x increases. Okay, numbers 19 through 24, I think, are the last set that we have here. Use a ruler or yardstick, I have neither, to find the heights and arm spans of 5 people. Okay, this is one where I have to make up numbers, and I don't know which ones are good. I might just ask ChatGPT to give me 5. Make a scatter plot, then draw a line of fit for the data, interpret the slope and y-intercept. Okay, let me do this. Give me 1 second. Okay, I'm opening up a ChatGPT window here, and I'm going to ask it to do what? Use a ruler or yardstick to find the heights and arm spans of 5 people. I guess we should do inches. Oh, their heights as well. Okay, so we can do both them in inches. Okay, so I'm going to ask it, generate 5 random human heights in inches and their corresponding arm spans in inches. Attempt to be within real measurements, realistic measurements. Please. All right, let's see what it does. I have no idea what's going to happen. Okay. So when they say arm spans, I thought arm span just meant from one to the other. I think they mean entire wingspan tip to tip. At least that's what they're doing for these arm spans. Because I was going to say, there's no way that this is going to be 65 inches if I'm 65 inches. I think they mean here and here. And I think that's actually normal. I believe that the majority of people have the same, they say your wingspan is about your height. That's not always true, right? So this is kind of like this. And these are pretty within, let's see if that's how we want to do that. Sure. The only thing is now when we graph these things here, okay, here's what I'm going to do. I'm going to copy and paste this one into our set. All right, hopefully that showed up for you and you saw everything there. I think you did. Let's copy and paste that. It's because that's going to be like our table data. So height will be X, how about? And their arm span will be Y. So let's make this kind of a table. We got our X and Y. Now when we graph this, keep in mind, I really got to change the scale of this thing. This only goes from about 65 to 70. Oh, it's 72 rather. Let's see. So what did they do previously on something like this? They would go, I have to think about this one. 65 is the lowest, 72 is the highest, right? So let's go like, I have to think about, sorry, I have to think about this one. Obviously, we don't want the 5 and the 10 there, so I'm going to wipe those out actually completely. Okay, now what the book did, and I didn't quite do this that one time, but I'm going to place 0 on these ones. They're not going to count for anything, and they kind of just do this little squiggly thing to say, okay, this goes from 0 to whatever minimum I want to do next. So how about 65 goes here, and then 66, 67, 68, 69, 70, 71, 72. So I'm going to place 72 over here, and then, yeah. So hopefully I can do the count with that afterward, but that's 72 here, and that's 65 there. So 65, 66, 67, 68, 69, 70, 71, 72, right there. It's kind of awkward. They're awkward numbers, right? But we'll deal. Now our values are, can you see it all? So 65, 65. That's actually literally a point that's on here. And then 70, 70 and 70.5. Here's 72, 70, 70.5 right there. Thank you, ChatGPT. 68 and 67.5. 65, 66, 67, 67.5. 72, 72. And 66 and 66.5. Okay, so positive trend. Draw the line of fit. Two above, one's below, but it's a little farther out below, so that kind of works for me. Maybe we just kind of do just on those 2 points, and then it needs to go a little bit higher, I think. So this might not be a perfect. That one's below, or that one can be on. That one can be on, and then this one, oh, what did I do that last time? Let's see. Part of what I'm doing is I want to make a trend line that also, it's not bad, it's just not perfect on that. I need something that's slightly below like that as well. My goal is to go right on here. Okay, you know what? I'm going to go right on here. I know there are 2 above and there's 1 below, but the one that's below is a little farther out than the 2 that are above. It's not perfect. I don't know if I'm giving you the best example of that, but ChatGPT did give me these values randomly, so who knows if they're perfect with it as well. So I'm going to give these points, 65, 65, and 72, 72. It is what it is. And this will kind of align with the ideal thing for what this thing does. They say interpret the slope in y-intercept. That means that we have to actually come up with the line. It says draw a line, but we need to come up with the line. So this equation is pretty straightforward, guys. Our slope is a rise of 7 over a run of 7, which is 1. 1 over 1. And as you can tell, I mean, I'll introduce it by using point slope form. Let's use x1, y1 right here. Y minus y1 equals m times x minus x1. When I distribute a 1, obviously there's no change in that. But when I add 65 over, negative 65 plus 65 is 0. So you get an equation that says y equals x. Very strange one, but that also means y equals 1x plus 0. That's the equation. The idea behind this is the y-intercept says when you have no height, you have no arm span. A human with no height has no arm span. That's pretty much it. Slope is a little bit different here. It says every inch you grow, every inch a human grows, their wingspan, arm span, also grows 1 inch. And I think that's just the idea, right? That's ChatGPT gave me some random ones that seem to be really close to each other, if not right on point, and that seems to follow along with our trend of that. Maybe I forced it a little bit, but that's the idea. Our wingspan is about the same as our height. I don't know if mine is. I haven't tried it, but yeah. Number 20, thought-provoking. A line of fit for a scatter plot is given by the equation y equals 5x plus 20. Describe a real-life data set that could be presented by the scatter plot. So remember, we're thinking about data here. Now the slope is 5. That means every time that you increase x by 1, y increases by 5, and you start at 20 for whatever this is. We could do something like you would get 20% on a test if you studied 0 hours. Or you completed 0 assignments during the unit. Let's do that. Let's let x represent the number of assignments completed in a class unit, and y represent the unit exam score percentage. So here's the idea. So interpreting slope and y-intercept, the slope is every assignment completed would lead to an increase in unit exam score by 5%. So if I completed 1 assignment in the unit, I'm expected to get 25% on the test, 2 assignments, 30% on the test, things like that. I guess it's a massive unit with a lot of assignments. I don't know. Or how about activity? Every activity completed. I don't know if they're more, whatever. That's fine. We'll include classroom and homework activities. Let's hope that you do the stuff. Now the y-intercept states that if you complete no assignments, completing 0 assignments would lead to a 20% exam score. Now, are these perfect? No, this would just be our trend line for this thing. There's a positive trend line with that. That's the idea, making it up. All right, number 21. Writing. When is data best displayed in a scatter plot rather than another type of display such as a bar graph or a circle graph? Well, a scatter plot really compares 2 things. Well, yeah, a scatter plot is really just a comparison of 2 variables. And as one increases, what happens to the other? Quantitatively so. So a scatter plot is best. Scatter plot's not one word, right? Trend line is 2 words. Scatter plot is 2 words. A scatter plot is best when comparing 2 quantitative variables. Quantitative meaning numbers. As something can increase, what happens? Being able to determine what happens to y as x increases. I think that's really the best thing there. The other ones can be qualitative. The other ones can just be for a single variable. And then, well, I guess percentages within that variable and things like that, right? A circle graph, I'm thinking of a pie chart. So I think that's best for scatterplot in those situations. All right, number 22, how do you see fit? The scatterplot shows part of a data set and a line of fit for the data. 4 data points are missing. Choose possible coordinates for those data points. Okay, so the way that they were kind of saying things before for these is, well, we want to make sure that we kind of keep this thing as it was. So I have a point that's on the line, another point that's slightly above it. These are slightly above, that's a little bit more above. That's slightly below, this is significantly below. Maybe we need another point that's a little more significantly above, like this one. Another one that would be below to maybe counter that a little bit, like this one here. We just need to make sure it fits the data stuff. We can obviously choose one that's on the line, but I want to do one that I can tell what the actual point is. Actually, none of these I could tell what they are. I think I could tell what that one is, so choose one that's on it. What else would seem to fit that trend? One more, let's see, 1, 2, 3 above. That one's barely above. 1, 2 below, 3 below. Maybe another one that's just slightly below. Maybe like this one right here. So I'm choosing some made up points like this one. So my 4 that I'm going to do that seem to really still fit the trend, the one in the, I'll go furthest left to right. Furthest left to right. So at number 22, I'm choosing the points. This is how I see it. 4, 40. I was trying to choose there 10, 80. That was my intent on that one. 12, 120. And this one's kind of a rando one. The X is 14. What would the Y be about here? These are going by 20s. So this is 80 and 100, and that's 120. So 110's right there. Maybe around 105. I'd say 14, 105. And that can work out to me for that. Number 23 says, a data set has no correlation. Is it possible to find a line of fit for the data? Explain. No, because there's more than one. First of all, they don't form a linear trend. Second of all, there's probably more than one line you could draw that's just as trendy as any of the other ones, which there's no true trend. So no, because the data points don't have a linear trend. That's it. That's all. Last one, number 24. Analyzing relationships. Make a scatter plot of the data in the table. So this might take a while. Describe the relationship between the variables. Is it possible to fit a line to the data? If so, write an equation. If not, explain why. Well, I want to first look at it and see if there's something here. It looks like as x increases, remember this is an increase. We're going from negative to positive toward positive. Okay, it's like that. Y is decreasing. So I'm seeing a negative trend so far. X continues to increase here, right? This is really treated as one table. And Y is now increasing. So if these are made as one data set, I'm going to say there's going to be no trend. We have to plot it, but I'm going to say there's going to be no trend here. Now, that means we have to use the second quadrant as well as the first quadrant for number 24. And I'm going to have to play with scales quite a bit. So me plotting points might take a moment. But I think my answer, guys, is there's going to be no trend. I think it's the first and last problem for which we get to play with, first of all. But second of all, identify no trend within. Now, my x's, I know they go out to 15 and negative 12 and stuff, but it's going to be weird to change scales on the x's. So I'm just going to stretch it out the most that I can. Y's, on the other hand, I have to go up to 150. No, 226. Jeez. So I have to go by 226. What if this was 250? These would go by what? 25s? So we'll go 50, 25, 50, 75, 100, 125, 150, and 200, and 250 up here. All right, this is going to look a little strange. We'll see what we can do. Negative 12 is going to be a little off. Negative 11, negative 12 is over here. And up to 150. So 150, negative 11, negative 12, like that. So remember, my Y scale is totally different from my X scales, right? Negative 9 is right here, and 76 is pretty much where 75 is. I mean, I'm going to see no difference there. Negative 7 is at 50. Okay, good. So what I went by seems to be pretty good here. Negative 4 is at 15. I'm 25 is right here. 15 is 3/5 of the way up. So like that maybe. It's maybe a little high up, but that's okay. Negative 3 is at 10. 2/5 of the way up. Negative 1 is at 1. I won't be able to see the difference there, so I'm just going to place it on 0. And then we're in positive range for x. 2, 5, fifth of the way up to 25. So you can see here, it was trending downward. A little bit of a curve, but it was trending downward. Negative trend. You can still draw a line through that. Now we're seeing something different here. At 5, we hit 22. Just under 25, I suppose. 6, 37. 37. That's like halfway between 25 and 50, because 37.5 is the exact halfway. So right there. 752, just above 50. Schweri. In a way you probably couldn't tell. 990. It's 100. 90 is 3/5 the way up between 75 and there. And then 15. This is going to be out of reach, but 11, 12, 13, 14, 15, and up to 226. So sure, right there. But here's the idea, right? I can't draw a line through this that's best. I could probably draw a curve. Like, a curve goes through this stuff pretty well, like this, right? Boom, 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 boom. And there are such things. There's quadratic regression, things like that. Not for what we're talking about, though. A line of best fit doesn't seem to apply to this thing here, right? So they're saying, is it possible to fit a line to the data? If so, write an equation. If not, explain why. No, I cannot fit a line to this data here. No, because the data points, again, do not form a linear trend. Just like the last one. Now, they do tend to form a curve trend, and that's something you'd learn more in IM2, IM3, I forget which one, but either IM2 and or IM3 that you would have that, you could draw a curve for it, but not a line, right? A line here and a line there, but that doesn't work, and you can't just say like, oh, just have some above, some below like this. That's not the trend. That's not the trend. This has something else going for it. But guys, we just passed the hour mark. Either way, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Nice short section here, and hopefully the couple point slope forms that we did made some sense, even if I forced them on you. I think section 4.5, do I have a preview here? Let me find it. Section 4.5 is going to be on analyzing lines of fit, so a little bit more of what we were just talking about here in the statistics realm. Thank you so much. Take care. I'll see you in the next one.